Hello. This bit is about Euclid's division in Gaussian integers. Let's start warming up by reviewing Euclid's division statement just for ordinary integers. So it says that I'm going to change it slightly to maybe your familiar one, but in my version it will be saying that for any two integers, x and y, there will be two other integers, q and r. And there will be such that, say, y will be equal to some multiple of x plus this remainder r. And there will be an extra condition on the remainder saying that it is less than the absolute value of x. The justification for that version, quick justification, a geometric argument. So let's look at multiples of x. After all, we are comparing y to possible multiples of x. So q will be just some multiple of possible multiples of x. So suppose that here's our starting point, here's x, here's 2x, somewhere here's 3x, and our y sits somewhere in between. So then how to manufacture the remainder r? Well, let's treat multiples of x as dispensable, as zeros really. So then we can freely add or subtract multiple copies of x from anything we have, and by doing so we can hop between the intervals of length x and bring anything by this hopping motion down to here. So that is our remainder. Well, it's also here, but if we want to place it in the controlled region between 0 and x, that will be it. So that will be just transporting it by shifts, by copies of x, either left or right, depending on what y is. So you can quickly convince yourself that anywhere on the line you could then do these translations by the fixed distance x and bring any point down to this interval, and the interval will be also such that 0 will be included and x will not, because if it is x you can move it to 0. So this is a semi-open interval, and hence the condition that the remainder can be also assumed to be non-negative and bounded by x. There is another component to this Euclid's division statement saying that q and r can be made unique under these conditions, but will not be using it much. So if you remember how this is used, it is used in producing the greatest common divisor of two integers, and in eventually arguing that any integer can be factorized into a product of primes. So these are very useful properties, these are very useful applications, which do not really require the uniqueness of the remainder. So let's relax this uniqueness condition, and let's also relax the condition that r is no, let's do it later. So let's just start with the similar input now taken from Gaussian integers. So let's take two Gaussian integers, that in w. Now try to replicate this Euclid's division statement, saying that okay, there should be some multiple and some remainder, again in the same arithmetic domain of Gaussian integers, the relation making them the quotient, sorry, it's not y, it's z now, or rather, let me make a w, and then I will be dividing by z, and I will be counting the number of copies, and then the remainder will be whatever will be left. So the crucial condition for that to work, for everything, so for Euclid's algorithm to stop and produce us greatest common divisor, is that we have this bound on r. So the r is not is less than what we divide by in some sense. So we'll have to manufacture this sense. We have to invent this sense for Gaussian integers. And the most straightforward is to use absolute value. But another useful property of the absolute value of x is that it is a natural number. And so I is a natural number, really, and then we always have stopping points because of the natural nature of our remainders. So if we just use the absolute value, it will not be an integer or a natural number. It will be, it could be some square roots. Let's use the square of the absolute value instead. So let's modify this boundedness condition by saying that the squared absolute value of r, which is called the norm, is bounded by the squared absolute value of what we divide by. So here the norm of that is squared absolute value of z is a complex number, and it is, if z is written as a plus ib, that will be a squared plus b squared. So for any Gaussian integer, the norm will be also an integer. And moreover, it will be a non-negative integer, and hence we have this. So again, we have the bounds from below by the nature of the norm, and we have now for the remainder, for the norm of the remainder, we have the bound from above. So let's argue this. That will be a version, a replication of Euclid's division adopted for Gaussian integers. So let's argue this. Let's first argue it in a similar fashion to what one can do with integers by translation, moving any integer to a fixed region of possible remainders, remainders to be. So let's look what we can do with translations by copies of that. So let's list copies of that, but copies now are counted not by an integer q, but by a Gaussian integer. So let's see what happens. Let me draw complex plane, and integer points on this are my Gaussian integers. One of them is called z. So then I can draw a line through the origin and this. And then integer copies of that will be on this line. So there will be here, there will be somewhere here to make it symmetric. There will be negative z, and somewhere here. Here will be 0 copies of that, so here will be 2 copies of that, and so on. But that is not all we can do by producing copies. Again, the quotient is a Gaussian integer itself, so we can have a perpendicular direction. We can go into the orthogonal direction, passing through q, moving the same step, and ending up with, well, let me start it here. So if I take my z and multiply by basic Gaussian integer I will end up in here. So that will be the place for I times z. That will be the place for the sum of I, z and z, so there will be the place for 1 plus I copies of z. And again we have a line here, and we have a line here, and we have a grid of all the copies of z. So here we will have, let's start with this one. So what we have here is negative, obviously negative I z. So this point is the sum of the two. So that will be 1 minus I times z. And say here we have the negative of that, so that will be negative 1 plus I copies of z. And continues forever, so that will be the analog of this grid of integer multiples of x. So that is supposed to be 2x, right? Integer multiples of x, and here we have Gaussian integer multiples of z. The same argument we used before by translating by this step or this step, we can bring any number on the plane down to, say, one region. Let's fix this square where we can bring anything in. And again, as before, it is semi-open, so these two, if we include them, we can safely exclude these two ends, because these two sides, because they will be translatable down to this side. So that is what we can do by translation, just anywhere in Gaussian integers or in more complicated arithmetic domains. But what we are after is this bound using the norm. So let's see what the geometry of this norm is. So norm is a square distance, and we fix the square distance to be equal to the distance of that, square distance of that. So then this will be the same distance, this and this. They will be sitting on the same distance, and all other points will be sitting on the circle of that radius, because for the points to have the same square distance is the same as to have the same distance. So I will just draw a circle again as much as I could. It's a bit squashed, but it's supposed to be a circle passing through these points. More circular circle. So that is the positions of all, not necessarily Gaussian integers, but Gaussian integers will be inside it. So all integer points, all integer coordinate points inside the circle will be Gaussian integers, good for being remainders. Well, I have my remainders safely placed in this region, so it is here, and a big chunk of it, more than half, is inside my circle, so I can treat them as remainders. But there is something, there is this region which is outside of the circle. So I can not claim them to be remainders in the sense of this norm. The norm of them will be larger than the norm of that. But I still can do my translations. So yes, this square was very convenient for translating everything in, but now I want to translate everything inside the this fixed circle. So I can take this region which is outside the circle and translate it by, say, moving here and then moving downwards. And what I will end up with is this part of the circle. So that is this bit, and it is being translated into this bit. Now I'm inside the circle. Now everything is firmly inside the circle, so I have a geometric argument in favor of this version of the Euclid's division. The fact that I'm using the norm to measure the smallness of the remainder is reflected in the name, so the Gaussian integers are technically called norm Euclidean. And here we can also say it in terms of the norm. So the norm is just the absolute value for integers, and we still can have this inequality stated there. So that is our conclusion, that Gaussian integers are norm Euclidean. So we have it's open for the whole sequence of statements standard in the story of integers to be translated to Gaussian integers, ending up with the unique factorization of any Gaussian integer, the fundamental theorem of arithmetic for Gaussian integers. It will also have interesting twists. The primes in this factorization will be, will deserve the investigation, so please stay tuned.